Hi, today we're going to focus a little on satellites. So first thing we're going to talk about is launching, so escape orbital speed. So figure out how fast something has to be going to be able to escape the gravitational field of a planet or moon or other large celestial body. So escape orbital speed is the amount of speed required to escape. In most cases, we'll be looking at Earth's gravitational field. Now, in order to escape Earth's gravitational field, an object must have a kinetic energy and potential energy that, when added together, is greater than or equal to 0. So from this, we get our kinetic energy plus potential energy is equal or greater than 0. So 1/2 mv squared minus g m1 m2 over r is greater than 0 when we substitute in our kinetic energy and gravitational potential energy formulas. Now, if asked for an escape speed, the question is simply asking for the minimum speed to escape, and we change the sign to an equal sign. Anything higher than that speed, and it will continue to escape. So, example, if an unknown planet has a mass of 7.08 times 10 to the 25 kilograms and a radius of 2.00 times 10 to the 7 meters, what is its escape speed? So, information we have got the mass of the planet, we also have our R value, and we're looking for V. So, we have EK plus EP equals 0. We can substitute in our equations for that. So 1/2 mv squared minus g m1 m2 over r. I'd move our gravitational potential to the other side of the equation. So we can start isolating for V. And then the mass of the object that's escaping will cancel out. Then multiply both sides by 2 to get rid of the 1/2, and then take the square root. At this point, substitute our values in, and then follow bed mass to calculate, and we should end up with 2.17 times 10 to the 4 meters per second. Next example, in order to escape an unknown planet, an object must have a velocity of 5,000 meters per second. If a planet's radius is 3 times 10 to 6 meters, what is its mass? So once again, write out what we have. So we've got 5,000 meters per second and 3,000 meters, or sorry, not 3,000, 3 million meters. We've got EK plus EP equals 0. We'll fill in our formulas just like with the last equation. We might as well move potential energy to the other side, cancel out the mass of object that's escaping, and then we want to solve for the mass of planet, so that's m2, so we need to rearrange to get that on its own. So I would multiply both sides by r, and then divide both sides by g, substitute our values in, and following bed mass, we should find that it has a planetary mass of 5.62 times 10 to the 23 kilograms. Okay, so we looked at escape speed. Now we're going to look at satellites in stable orbits. So in order for a satellite to stay in orbit, our centripetal force must be equal to our force of gravity, and they must balance out. If they are not balanced, one of two things will happen. One is the object will get closer and closer to Earth, eventually coming back to it, or it will go in wider and wider orbits and then eventually disappear out into space. So using those forces being equal, and ME being the mass of Earth, MS being the mass of the satellite, and R being the radius of the satellite, we get the following. Our force centripetal is equal to force of gravity. So we've got S v squared over r equals g me ms over r squared. You'll notice that one side's divided by r, the other's divided by r squared, so we can cancel out an r on both sides. We also have mass of satellite on both sides of the equation, so we can cancel those out as well. Now that gives us a simplified formula that for a satellite in orbit, our velocity squared is equal to a gravitational constant times the mass of the Earth divided by our radius. So looking at an example, we have what is the speed of a satellite in orbit around the Earth with an orbital radius of 7.5 times 10 to the 6 meters. So we've got mass Earth is 5.98 times 10 to 24 kilograms, and our radius is 7.5 times 10 to 6 meters. So we've got force centripetal is equal to force of gravity. We'll do those same steps as we just did on the previous page. And now we want to know what the speed is, so we'll take the square root of both sides, substitute our values in, and we get that the satellite is moving at 7.3 times 10 to 3 meters per second. Okay, next we'll talk about period of a satellite. We can utilize our equation for velocity of an object in circular motion and the equations we have been looking at so far to calculate the period of orbit. So for example, what is the orbital period of a satellite with orbital radius of 6.9 times 10 to 6 meters around the Earth? So we know we're using the mass Earth, so that's 5.98 times 10 to 24 kilograms. We know our value is 7.5 times 10 to 6 meters. And we're looking for a period. So once again, we know force centripetal is equal to force of gravity. We can use msv squared over r equals g me ms over r squared. And then we arrange to solve for v. Now we know v is just our circumference divided by our period. So we can take that and substitute into our equation. Now we're trying to solve for our period, so I'd multiply both sides by it to get out of our denominator, and then divide both sides by the square root. At this point, substitute our values in, and we get 5,700 seconds.